I am delighted to introduce to you a three-speaker presentation today. Erica Middleton, the director of the Language and Learning Lab, Anna Krason, who is a postdoctoral fellow in the lab, who I assume will be joining us online, and Matt Ambrogi, who is a clinical research coordinator. And they're going to be giving a talk called an electrophysiological investigation of speech error monitoring in individuals with aphasia. Erica would like hold big questions, discussion questions for the end, but feel free to interrupt with clarifications. Thank you.
Great. Thanks, Laura. All right. We are grateful to Nancy and Marc Shrier to make this Shrier Family Topics in Rehab Science possible. Grateful for their support and belief in our mission. I'll leave this up here for a little bit so people can write down the CME credit code. The planning committee members and ourselves, we have no financial relationships to disclose. So the objectives today, the audience members should be able to describe different kinds of common errors in naming in aphasia and how they are generated. You should be able to define event-related potential and error-related negativity and discuss the challenges of isolating ERPs during speech production in people with aphasia. I wanted to give acknowledgement and thanks to our major collaborators, Abhijit Patra, who is at the Manchester Metropolitan University in the UK, and Zhanghan Qi, who is at Northeastern. So just to give you a little roadmap for what we'll be covering today, we'll be focusing on the phenomenon of self-monitoring of speech. And we'll talk about its function, and hopefully I'll convince you that it's pretty interesting. We'll be talking preliminary results of a feasibility pilot study of 10 people with aphasia, where we focus on EEG and the self-monitoring of naming errors in these individuals. And then Matt will finish with tips and tricks for collecting high quality EEG data in people with aphasia. So I think it's always more illustrative to give examples of what I mean by a particular phenomenon. So here's an example of a speech error that was monitored. If you recall, we had a former president, George Herbert Walker Bush, who stated the challenge facing the United States is that we have to be right one time. I mean, 100% of the time. So that was fortunately caught by the speaker and repaired. An example of a speech error monitor that was not monitored is this was Vice President candidate Sarah Palin, who said erroneously, but obviously we've got to stand with our North Korea allies. So self-speech monitoring is pretty important. It can avoid, in some instances, cataclysmic events, but I'm sure somebody else caught her error for her and headed off a foreign affairs disaster. But error monitoring speech ameliorates misunderstanding. And what we know about how speakers monitor their speech is we know that they do it through the ears. So external monitoring, that's usually after the fact, after an error has happened and they repair it to variable degrees. But we also know that there's internal monitoring. So evidence comes from, it's a very old literature. It stems back to the 80s. And there's many different paradigms, but one of the interesting ones is this approach where you are priming people to say a phrase that's a spoonerism so that you switch the onsets. And what you find when the switching of the onset would lead to a taboo phrase, for example, toolkits, you fill in the gaps. But what you see is you do have suppression of those relative to the control condition, and you also do have electrophysiological signatures as well. There's also many observations of The ability of speakers, so as soon as they interrupt an error, they have the repair ready. So that says that they either detected the error before they said it, or simultaneously they started to prepare the repair. So there's a lot of phenomena supporting this internal monitoring. So I'm going to talk about really two primary theoretical approaches to how we do internal monitoring, and I'll nod towards a third one. I'm not going to talk about that much, but Levelt, he kind of laid the empirical and theoretical groundwork for his perceptual monitoring model, and it's still pretty popular because of its simplicity. It says essentially that we are not really privy to intermediate stages of production, and that we use the perceptual system to do both internal and external monitoring. So this is the phenomenon of inner speech. So in the internal loop, basically you have the end product prior to articulation. It's a phonetic or a phonological representation that is conveyed to the perceptual system and then to a conscious central monitor. And that presumably you are listening in inner speech to this phonological representation and you stop it before you articulate an error. However, there's a host of work suggesting that, well, it's probably not that simple. And these production-based monitoring accounts suggest there's many different views, but the notion that there are monitors associated with the subcomponents of the production system, and I will be cashing this out more specifically in terms of one computationally explicit and very influential model, the conflict monitoring model later. And then, as I said, I'm just going to nod towards a third class of models that maybe at the end, we can talk about the connection to our results. But this is a speech as action model, and they talk about forward models. And yeah, so Erin and Amanda and Laurel, maybe we could talk about these, but they are pretty perplexing. And so it just would be fun to talk. So errors monitoring in speech. So we are an aphasia lab, and people with aphasia are prone to production and comprehension-based errors. So this variability in in their abilities has led to just rich data that has informed models of monitoring. So for example, we have observations in the literature that militates against Levelt's conceptual or perceptual view, instances of poor comprehension in people with aphasia, but intact self-monitoring. We also have some other observations of lack of correlation between comprehension abilities and self-monitoring abilities. We can talk about, how truly difficult it is in Levelt's theory to account for such results, but it's just to illustrate that aphasia is a wonderful domain to study to answer questions. There's also clinical implications of self-monitoring aphasia. There's an early body of work by Marshall and colleagues. For example, they found that people with aphasia in the acute or subacute phase, when they showed better self-monitoring ability, that they actually responded better to treatment. And then in our own work, we were able to explicitly because you could expect that people with better self-monitoring might just be, less severe overall, right? So, but we were able to show that, in fact, self-monitoring of naming errors actually does lead to learning and improvement in future naming trials. Yes.
How was self-monitoring defined in these studies?
Well, it depends. Depends on the study.
Some example.
Yeah, no, I mean, some of them are, they'll play them back to them and then they will say whether they made an error. So there's explicit monitoring measures and there's implicit monitoring measures. So for example, in our work, we do implicit because we just code after the fact, whether they show overt instances of detection. And we'll show you our coding system in a bit, but it's a big mishmash and there's issues, I think, with the explicit monitoring assays. For any number of reasons, right? Could relate to working memory or attentional problems or instructional, comprehension issues. So now I'm going to switch gears and tell you a little bit about naming in aphasia. This is a major focus in my lab. There are two main types of naming errors that have received a great deal of psycholinguistic attention as well as in aphasiology. The first kind of major type of naming error is semantic naming errors. And so these are instances where instead of the target, you produce a close semantic competitor. So for example, for lighter, you might say matches. For wing, you may say arm. For cow, you may say horse. And for crown, you may say throne. And these contrast with a second type, which we think about as it is successful retrieval of the word, but then something goes wrong when they are retrieving and assembling the phonology or the sounds for that word. So these are phonological naming errors. So kangaroo, kangaroo, bobot, swirl, and hammock, some examples. I'm going to give you a sense of a major theoretical framing or understanding of where these errors come from. So this is the two-step interactive model of lexical access for oral naming. And it is a two-stage model where you get mapping from distributed semantic features to an intermediary level, lexical level. We call this the lemma. It's a pre-phonological abstract representation, but the completion of that level we call that word selection. Once the word is selected, then you have activation that spreads down to the phonemes, and then you have phonological spell out. But what's important about this framework is that they are relatively independent. They are interacting, but they're relatively modular stages. And in people with aphasia, errors are understood to originate differently from these two stages. So we have our semantic error, dog for cat, and also a semantically and phonologically related error, rat for cat. These are generated from that first step of retrieval, so word retrieval or word selection errors. We have an interesting kind of mixed case. So formals are real words that are phonologically related to the target, but not semantically. And what we know about these error types is that they are generated both at the word level and the phoneme level, but it depends on the person with aphasia. For some individuals, it can be more at that first level, but in my research, preponderance of these can be attributed to the second level. And then we have non-words, the classic non-words, so jat for cat. But what's kind of the core mechanism for how an error is made at either of these stages is activation in a target that's just close enough, in a competitor that's just close enough to the target that it surpasses some kind of threshold and is selected instead. But what's interesting is that what that provides is this kind of it's about conflict or activation patterns that might be a signal for error monitoring. And so that's where the conflict monitoring model comes in by Bonnie Nazari and Gary Dell and Myrna Schwartz. So semantic weights and phonological weights, these are the strength of the connections in the two stages, okay? And individuals with aphasia can have variable impairments in these two weights, we'll call them weights. So in the Nazari model, they capitalized on, as I said, this conflict between representations. And they operationalize that as if you have a highly active unit that is not the target, how active are the rest? Or they also looked at a different version of the model, how active is the next most highly activated unit? And they propose that it's this conflict between representations, it's kind of naturally occurring competition that might be a signal for error monitoring. And in their theory, it is this conflict that alerts the central monitor. So they do invoke this domain general, central monitor processor that comes online when it detects conflict in this more modular system. And the evidence for their theory includes that the integrity of the weights at a particular level. So people with good S weights are really good at monitoring semantic errors. People with good P weights are good at monitoring phonological errors. Something to do with just the integrity of the signal, right? So strong weights makes a clearer signal for when conflict is actually related to error creation. So, but in our work, so heretofore we've only focused on overt monitoring coding, which I'll show you in a minute. But what about the internal monitoring signal? What if, instead of relying on the instances in which people with aphasia overtly monitor, maybe they are monitoring these errors, to greater rates, different rates internally. Can we get at that? And I think if we can assay that, it might, lead to greater clinical application of EEG in people with aphasia, right? So we're going to assay the internal monitoring of semantic and phonological errors in people with aphasia using EEG. So EEG, I really am not the person to be speaking about this slide, but I will try. Okay. All right. So it is, okay. So it's activity, it's neural activity or electrical changes, but we relate that to neural activity. And so EEG is measuring that over a time period. But what we're interested in is ERP. So it's event-related potentials. So it can be either the presentation of a stimulus or it can be your own response. And you time lock shifts in potentials around that specific event. So in this study, we're going to be looking at the onset of errors, semantic errors and phonological errors in people with aphasia. We are primarily interested in error-related negativity. So there's a huge literature on this in other domains of performance, suggesting that this is a negative going waveform that starts about 50 milliseconds before the onset of the error. And it goes to about 100 milliseconds after, or sorry, no, it peaks. It peaks around 50 to 100 milliseconds after an error is committed. But what we know in speech studies and other domains is that it localizes to the anterior cingulate cortex, which is implicated in error detection and conflict monitoring in general. So this will be some of our study, and I think, Matt, you are up. Oh, wait, sorry, predictions. Sorry, before I jump, okay, predict. All right, so predictions, fun in a pilot study, right? Feasibility study. But in a perfect world, we were like, this is going to be so cool. We're going to get such clear patterns. It's going to be so interesting. So in a perfect world, let's imagine that noise is not such a problem. And we might predict that in conflict monitoring, that you would predict that you'll see an ERN for both types of errors because the basic mechanism is conflict, right? But you might expect an earlier ERN profile for semantic errors because when a semantic error is committed, it also has to go through phonological retrieval and assembly. So we should see a slight shift earlier for the conflict monitoring model. The comprehension model, they probably could contort their theory so that they would predict an ERN for phonological errors. But I think with the semantic errors, though, because it's internally it's phonology, and then it's perceived internally, and then you retrieve the semantics. So I think that the semantic errors should show later iconic waveforms. So for example, these perceptual EEG components, P200, P300, and N400. So Anna can speak more about these components. Now, in the real world, we actually run the study. I think we'll be happy if we see anything that's interpretable. So to the group or individual, people with aphasia show an ERN for either type of error. And I'll put it out there that perhaps different people with aphasia do monitor the two errors differently. Now you're up. Yes.
Quick thing. So I wonder if the complexity of the meaning and the difficulty in pronouncing a word might change that retrieval to production time. So it's not always like a fixed, just
Yeah. So
or if it is, it's kind of
what I can say about that, I like there's theories that you buffer Like there's like articulatory buffer. And so if some, things are prepared earlier, but you're still working on other elements, that it waits for a certain kind of length of a phrase, and then you start the articulatory process. There's some theories like that, but interestingly, militating against the perceptual view is that they estimated that you actually would only have 150 milliseconds around there to inspect the inner phonological stream, which is not enough time. It's not enough. And we find there's some studies where they make speakers speak faster. So you'd expect that if they're speaking faster, they'll be slower to detect, or they'll detect to less rates. And actually they detect at the same rate, and they detect faster. So everything revs up together. Yeah, so it's an interesting question.
Yeah.
Thanks, Don.
Hello. Let's talk about methods. Rest assured, any speech errors that I make in the fullness of this presentation are illustrative. So we had 10 people with aphasia. We analyzed 8 data sets due to noisy data. We'll talk about that a little later. They were profiled from a large group of participants who, based on their problems, based on their lexical access deficit, which we defined as problems with retrieving words or word forms during naming. They had good lexical semantic comprehension, they had good word repetition, and minimal apraxia. We recorded EEG during presentation of images from our common objects corpus. We had 300 images which were administered twice. And those images had very high name agreement, which is important because we really want to be looking at just genuine speech errors and not like dialectal variation or anything like that. And then we processed the data focusing on semantic errors and phonological errors, as Erica mentioned. And that is accomplished by coding. We take the transcript of their speech, and then we code all of their utterances. And so in that way, we can identify what type of errors they make. And then we are able to identify the onset of the speech error and then map that to the EEG waveforms. And that way we can see what's happening immediately after they make an error to see, hopefully, if they've detected it. And we apply this overt error monitoring coding system that Erica mentioned. So the way that works is, here we have an image of, well, I suppose that's a wrench, but the participant might say screwdriver. That's an example of a semantic error. And if they just say the word screwdriver and nothing else, then that's an error that was not detected. They could, however, say screwdriver, wait, no. And in that case, they've detected the error, but they've not repaired it. They haven't corrected it. They might say screwdriver and pliers, and they detected it, but then they did not accurately repair it. Or they might say screwdriver wrench, in which case they have actually corrected it. And then we have an image of a yo-yo, and we might hear the word lodo, which would be a phonological error, which was not detected. And then there's a handful of ways that they could detect and correct, or not correct, or repair or not repair. So I'm going to talk a little bit about our actual EEG setup, the kind of nuts and bolts of actually hooking somebody up and getting them running. So we measure the head, we measure the circumference of the head, and then we seat the cap on the head using a measurement from the brow line that is derived from that circumference. We attach reference electrodes to the orbital ridge right here next to the eye, and also the this little protrusion, bony protrusion behind your ear, which you can feel there. So we attach to those locations because there are very few muscles in those places, and you can feel that you're basically just touching bone through your skin. Muscles generate an electrical current, and when they activate, and that can corrupt the signal from our instrumentation. Those references are located next to the eye and behind the ear because when you speak or blink, you activate these muscles in your face. And so we can take that electrical signal and we can use it to sort of cancel out what we see in the actual data stream later. So if because this is sort of the cool thing we're doing is taking data from people while they're speaking, you have to activate all of those muscles to speak. So if we can take that interfering data and remove it, and we can hopefully, ideally, get clean data. We gel and plug. So we put the cap on after we've attached those externals, and then we gel a set of ports in the cap, which has all these little ports in it, and then we go through and we hook them all up systematically and in parallel. And then we plug the electrode array into the amplifier, which we then energize, and then we can actually see the raw data stream coming through, at which point we can go through. We take away the phone, of course, from the participant, and anything else that generates an electrical field we remove from the room. And then we go through and fiddle and zhuzh. You look at the data stream, you see what's looking weird, you fiddle with it, and you zhuzh it. That's that.
I was wondering if you had mentioned briefly during the talk that the ERN can precede an error as well as be before it starts.
The negative inflection in some
Yes.
studies can start as early as -50 milliseconds.
And did you, because you then went on to say you looked after an error.
So
Was
it
your time
peaks-
window
It
including?
peaks at,
Mhm.
across the literature, it peaks at 100 minutes.
But yeah, really excited to be still able to tell you a bit more about the data analysis and results for the study. So let's jump right into it. I'm going to tell you a little bit more about how we pre-process the data. I'm not going to be going into too many details, so if you have any questions, please let me know at the end. But basically, we recorded the data from 32 electrodes. And we dealt with the artifacts in the following way. So we use a high-pass filter to remove any skin potential artifacts, then low-pass filter and a special algorithm to remove any muscle-related artifacts. Finally, we used independent component analyses for eye-related artifacts and peak-to-peak voltage of 150 microvolts to remove any other signal noise. And we segmented our data into smaller chunks called epochs that were basically from 500 milliseconds prior to the response up to 1000 milliseconds after the response was made. And we use a baseline correction of -400 to 300 milliseconds to kind of establish a common starting point and also reduce any other slow drifts in the data. And in terms of our ERN analyses, so as Matt mentioned, we analyzed the data for 8 participants. This is because one participant didn't complete the full experiment. And then for the other participant, we actually dealt with, we had some synchronization problems with the data. So I'm presenting you the results for 8 participants, and we did group and single subject analyses. And for these, we used linear mixed effect regressions, where our dependent variable was the mean amplitude within a specific critical time window, which was from -100 milliseconds to 100 milliseconds. And then our independent variable was the correct versus semantic errors in one model. And then in the other model, we used correct responses versus phonological errors. And here I'm just showing you the distribution of the electrodes that we collected the signal from, and the red dots means these are the electrodes we used for the analyses. And this is based basically on previous literature looking at the ERN effects, and these include mainly frontal electrodes, but also a little bit of central electrodes as well. And to kind of establish the relationship between the ERN effects and the behavioral performance of our participants, we also ran Pearson's correlation analyses. And this was done between mean amplitude within this critical time window and detection rate of phonological and semantic errors. And these correlations were done separately. Okay, so on to some of the results. So I'm going to be first showing you group results. Here what I plotted is the mean amplitude within this critical time window that we analyzed on the y-axis, and then in colors you have different responses. So we have correct response in gray, phonological errors in orange, and then semantic errors in blue. And what our analyses showed is that we see a significant difference between phonological errors and correct responses, meaning that the amplitude was more negative for phonological errors than for the correct responses, suggesting an ERN effect for phonological errors. And we don't see such a significant difference between semantic errors and correct responses. And this result is actually also strengthened by our correlation analyses. So what's plotted here is a correlation between the error detection rate and mean amplitude difference. And what you can see here is a negative, pretty strong correlation for the phonological errors, but no such correlation for the semantic errors. Now, what we did next is we also looked at individual subject data. So here I just plotted, just for the visualization purposes, plotted each participant separately. And I'm going to focus on 2 participants in particular because they actually showed significant effects at the individual subject level analyses. So here we go. The first participant, P1. Here what you can see is that once again, we see this significant difference between phonological errors and correct responses, and no significant difference between semantic errors and correct responses. So once again, here at the individual level, P1 shows an ERN effect for phonological errors. Here on the right, I plotted the waveforms. So the first plot at the top, this is the waveforms with correct responses in black, and then the orange, once again, is the phonological errors. This is plotted for one particular electrode, FZ, which is at the frontal of the, it's one of the frontal electrodes. And the gray area is basically the critical time window that we looked at. So minus 100 milliseconds to 100 milliseconds. And as you can see here, there is this really nice time-locked difference between the 2 conditions. Here at the bottom, I also plotted scalp distribution, and this is what's plotted here is basically the mean difference between the 2 conditions. Blue means it's more negative, and red means it's more positive. So what you can see here once again is that this ERN effect, again, it's pretty much very much frontal. Okay, so now moving on to the second participant, P2. Here what you can see, so this is the data for the second participant. And here what we found is, first of all, we couldn't really analyze phonological errors versus correct responses because there were too few phonological errors made by this participant. But what we see instead is a significant difference between semantic errors and correct responses, such that, again, the amplitude for the semantic errors was more negative than for the correct responses. And this effect was significant, suggesting an ERN effect, but this time for semantic errors for this particular participant. And here on the right, I again plotted the waveform difference. So once again, you see in this critical time window that we see the difference between the 2 conditions, with semantic errors being more negative. If we look at the scalp map distribution, again, we see that this difference is located in the frontal brain regions. However, it goes a little bit more to the central regions as well. Okay, so on to some summary and interpretation of our results. Well, first of all, self-monitoring of speech errors by people with aphasia can be detected with error-related negativity. Oops. And in terms of phonological errors, we see it at the group level. So we see a significant ERN across the group. And this was also strengthened by our correlation results and basically suggest feasibility of the paradigm. And we think this may mean that ERN is related to overt monitoring rate. We also found a significant ERN effect at the individual level. So P1 showed a classic ERN pattern. And so now what does it all mean? Well, this actually, so our results are actually in line with broader literature on the anterior cingulate cortex. And the literature basically suggests that the ERNs are generated in the anterior cingular cortex. And we know that this area is actually associated very often with many cognitive processes, including motivation, decision making, cost benefit calculations, learning, but also conflict monitoring and error detection. In terms of semantic errors, so we only see a significant ERN effect for semantic errors for one participant. And again, this result that we found supports conflict monitoring model, but I want to point your attention to the actual result. When we look at the waveforms here on the right, I hope you can see my mouse. Basically, this effect is not truly time locked. So we can see this prolonged negativity going even up to 400 milliseconds or maybe even later, suggesting there might be some other perceptual effects. So maybe some semantic errors can be actually monitored by perceptual system. So as next steps, we're planning to explore other ERP effects, such as P300, which often actually occurs after an ERN and is related to cognitive processing, or an N400 effect that is related to semantic integration and occurs even later, so around 400 milliseconds. And in terms of future directions, we think a case study comparison might be a good avenue to explore, particularly when looking at behavioral and lesion profiles of participants. And this is to say that it might be the case, that the same kind of error can be monitored differently within an individual, but also across individuals. So it would be really great to check this out using case study comparisons.
So you had presented that errors could either be like self-detected and repaired or not, but were the data analyzed with that dimension of whether
We
an error?
haven't looked at that yet.
You haven't looked at it.
The maximal power, not over parseling the data. We first just started with detectors.
Because that could be interesting if there were
Yeah.
differences across the semantic and the phonological errors and the rates
Yeah.
of detection, and then
Yeah.
you can see if it was that kind of overt detection that
Yeah.
was monitoring some of the.
Exactly,
Yeah.
and that lingering effect, what
Yeah.
you said might have been perceptual, if that was a person who did a lot of self-corrections and monitoring,
Repairs, yeah.
that, right,
So
repair.
we also, we built in, I always like to build in redundancy in design, so actually we also can ask the learning question in this design as well. Cause we presented the 300 items twice. So we can look at, cause it's also, interesting,
Mhm.
like is the ERN a sign of any kind of improvement on the same item in the future, so there's a lot to do with that. Right, Matt, thank you.
Sure, yeah. So I'm just going to speak briefly about some EEG data collection consideration and tips. These are just some things if you end up in a position to be gathering EEG data with people who have had a stroke. It's just some things I've learned in the process of doing this to get better data. So first, before the session even happens, when you're on the phone with the participant, it's a really good idea to talk about hair, glasses, and clothing. These are things that don't end up usually in an actual formal screener, but they are important for the experience of the participant when they come in. Hair in particular, people have a lot of feelings about their hair, justly. And when people come in to volunteer for research, I think they do not typically expect that their hair will become admittedly non-destructively, but nevertheless very messy. And so I think it's a really good idea to talk to people about that in advance of them coming in, because you really don't want to be in the seat and being like, now I'm going to squirt a bunch of sticky goo in your hair, and they weren't ready for that. Glasses are also a kind of an interesting situation. Not a problem. You can definitely get good data with glasses, but you end up with the sort of temporal electrodes can be pulled off from the scalp a little bit. So that takes a little bit of finesse. And if participants do not require glasses to see the stimulus, then maybe don't wear them. And then clothing is another thing I like to talk about because really slippery synthetic materials that can generate a lot of static can generate a lot of noise in your signal. So I typically will ask participants to come in like an old t-shirt or something rather than something slippery. Fatigue and attention are really important considerations for this group. The setup can take a long time. It's quite boring. It takes place in a darkened room. We explicitly direct them to remain relaxed and to keep their face relaxed. And also a lot of the time, most of the time our people are somewhat elderly. And all of that can result in sleepy participants. So definitely adequate breaks are really important. Also, in terms of setup, we have 2 experimenters setting up always, and that enables us to move a lot more quickly. One of our experimenters can be gelling ports while the other one is plugging them in, so that goes a little bit faster. And then there's also a question of how many ports you use. So we use a 32 port setup. We're using 32 electrodes. You could use 64, 128. But obviously the more electrodes you use, the longer that takes, and then that whole process kind of can get really drawn out. So this is really sort of a cost benefit analysis with your own research, where you want to look at like, what kind of data resolution do I actually need? Do I need 128 points of data, or are we going to be able to get what we need from 32? Which is what we're doing. So that's that. And then, we also have a nanny cam. So there's actually a nanny cam in the room pointing at the face of the participant, just because we can't be in the same room with them at the same time. And that is really helpful to just see, are their eyes drooping? Are they literally falling asleep? And then you can offer a break, have a chat. And, I talk a lot about, when I'm talking about this stuff, rapport with the participant is really, really important, and having a really clear, open sort of channels of communication with the participant and building a relationship with them is really big in this work. And that is the kind of thing that enables you to, when they are getting really drowsy, you can actually get in there and have a conversation, have a chat, tell a joke, whatever, and tell a story, people like that. And that can, eliciting a laugh from a participant can actually really bring them back from I'm falling asleep, and make your whole process go much, much better. And then there's hair considerations. So we talked a little bit about hair already, but so baldness versus very long or very thick hair. Bald participants typically will have more oils on their skin. Oil is an insulator, and that can cause, that can impede your data collection. So we will typically, for a bald participant, wipe their whole head down with an alcohol wipe to remove those excess oils right before we get started. And that has really helped with getting cleaner data. Also, big hair, big cap, larger circumference, that can fiddle with that calculation I mentioned earlier from the brow ridge to where we actually seat the cap. So that's something you kind of have to take into account. And then also, big hair, like for example, I've run a participant with dreadlocks, huge, very thick, large dreadlocks covering their whole head. And that's not actually a problem. You can definitely get really clean data from someone with hair like that, but it does require kind of another step in which you take your sort of, your gel applicator, and you really have to like burrow down all the way to the scalp, move it around and make a little LZ for your gel, build a whole channel of gel back up to the top of the port. And that takes finesse and skill for sure, but that's really, I think, I've seen people really balk at that, and it's really not a problem, but it just, takes patience. And again, mention the hair in the screening. Also, people have, I've had many participants who go to the salon every week, and I schedule those participants on their salon day, so they can come in and get their hair all gunked up and then go straight to the salon and get their hair fixed. And people really appreciate that. It's kind of one of those respect for persons things I really kind of seek out. Comfort. We talked about room temperature, comfy non-rolling chair, not too comfortable, see fatigue from earlier, but comfortable enough. Shouldn't roll, back support, very important. And then production. So, we're asking people to speak, and like we talked about, speaking introduces noise. So the best thing I found for this is participant buy-in. So this is like, get your participant feeling like they're doing the science, like they're here with you. And so what we do is we get them all rigged up, we get the data stream running, and then we actually put the data stream on the screen in front of them so they can look at it and actually see the effect of the things that they do on the raw data. And we point that out to them. So I'll say like blink, 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 and then you can see all those blinks happen. And I'm like, that's how sensitive this equipment is. Like, you can see your blinks, clench your jaws, and the whole data stream turns into a wash of noise. And you're like, that's what happens if you clench your jaw. And so that really makes, first of all, participants, capital L, love that. But it also really makes them feel like they're part of the science and they're in on it. And then I've really found that that moves the needle on getting really nice data. And then comprehension, like with anything, you really, simply worded, clear instructions, good examples, and, open door communication, rapport. That's it.
Anybody else have any questions? I have another one, but everything. questions,
And Aaron,
comments? Yes.
So I know you talked a little bit about this internal monitoring system. And my understanding is that this is largely discussed in context of like events and errors occurring in the first place. Because you sort of have that ability to internally monitor, so before anything comes out, that system kind of should be able to.
yeah, I mean, it's in that context, but it's also kind of like this larger meta, kind of like control systems. Like control systems that detect errors and control the processes as well. So I don't know that the mechanisms that various models invoke are just for error detection or, for other.
Yeah, I was just curious because you kind of framed this as like, we want to go in and study this internal monitoring. But all of the errors that you're looking at could also potentially be externally.
Yeah, I think that's why, I mean, it's about, because we know that word recognition or we'll have to get into the nitty gritty of like really how fast can you recognize a phoneme, right? So, but I think because this connects out to a larger literature of the ERN and what the ERN means and how it's localized, just this huge literature. So I think that's why we think of it more in terms of conflict, but it is an issue that we're gonna have to deal with. But
So, I mean, since the correlation between the overt error detection and the ERN is at the heart of the study. I was wondering, and this is a kind of a statistical analysis question. I know it's possible to look at trial level data with ERP, albeit very noisy.
yeah,
Could you put detected or not overtly detected in the model as a covariate or as a factor of interest to see whether you can see any difference in the ERNs on a trial level?
yeah, so like, enjoy your approach of the cross-level
Mhm.
interactions, if we have enough data, because it is,
Mhm.
again, in any one person with aphasia, I know that their rate of detection might be something like 20 or 10%. And so you have to take, what was their detection behavior, how many, because most of the trial usually are just not detected. And so we're not gonna have a lot of observations, and then you take that and map it to what trials were actually phonological errors, right? So again, it's like this parcellation of data. We might, I mean, at the group level, I think it's worth doing at the group level.
Mhm.
You said you're using linear mixed effects modeling.
Yeah.
For that.
Well, logistical.
But you certainly wouldn't expect, I mean, if you had a 2x2 table of whether you see an ERN and whether an error is detected or not, even if it was a simple
Yeah,
chi-square, you'd expect there to be an association, in neurotypicals at least. Right, if indeed that's how if it's happening internally using the anterior cingulate system. So even that could shed light, if you don't see an association, maybe that would say, we don't know how you're doing it, but it could be through the external route.
yeah. It's an embarrassment of riches, this data set. I mean, it's, we were hoping that there's so much we can, but that's how we
Yeah.
find it. But I'm just trying to find that exception. Yep.
That was a terrific, almost like a stage show performance by people coming up and down. So very nice slides, and I learned a lot from that. So I'm wondering, so a simple question, just remind me, backing right up, what is the actual error that occurs, that there's two different flavors of error? What is it that you're actually detecting? And how does that relate to time zero, with this event?
Yeah, so time zero is the word, the spoken word onset of the target error, whether it is dog for cat or yodo for yo-yo. So it's time locked to the very
To the actual production of that.
the onset, yeah.
Right, so presumably there's a whole lot of stuff that happens to prepare for that onset. So time zero, and then the event related the potential that you see is 100, the peak was at 100 or so, is that right?
In the literature, but our window of analysis, is -100 to 100. That's our window.
Yeah, I was trying to understand why you would see like all of this earlier. Things happening before time zero, if that makes sense.
Yeah.
Well, I mean, on a production model, all of these production models, of which the conflict monitoring model is an example. The, if you will, inference copy or forward model of the preparation to produce a response happens is launched before the overt error is produced. When you say all this stuff happens before, I think that's part of what, and that's part of how an ERN could actually precede an overt error.
Yeah.
You need an account like that to accommodate how could the ERN possibly happen before an error? It's not just tuning in once you make an error. There's other, but there are other, and I don't remember this, Erica, aren't there different components that respond earlier versus later after an error that are supposed to be
Yeah, so
Tied
there's
to
also,
detection.
an error-related positivity.
positivity?
Yeah,
Right.
I think that might be part of the puzzle here as well. We're gonna start to look at that and what,
Mhm.
what those usually look like, when they start. So, because I think we are maybe seeing some positivity effects a little bit later. That might be,
Mhm.
that awareness there.
How do you account for the lesion location?
Anna, you looked at the lesion. Do you want to speak to that?
Yeah, absolutely. Well, we did look at lesions for the two participants, so for P1 and P2, and they, well, we didn't do any like overlap lesion calculations, but they do show distinct lesion patterns. So P1 shows. So P1 is the participant who shows phonological ERN effect, and this participant actually has a lesion. Most of the lesion is in the middle temporal gyrus, which would actually make sense because this region is often associated with phonological processing. And then the other participant, P2, who's showing a semantic ERN effect, this participant actually has a large lesion in the TPJ, so temporal parietal junction. So yeah, I think that one is a bit more complex and maybe also interesting to kind of quickly interpret. But yeah, so we checked the lesion location, but we didn't do any proper lesion overlap analyses.
Okay, sorry, I was wondering about more, how do you account for it in your data analysis?
Yeah, that's a big old question of anybody that does EEG or stroke. I mean, I don't know of any systematic approach to do that. I think we'll see, if you can kind of just talk about, well, it's kind of frontal or it's kind of posterior, or it's still, like the level of localization popped up with no evaluation.
But both of those subjects, the anterior cingulate is presumably spared.
Sounds like it.
So you would be able to detect the ERN if the generator of the ARN is there.
I have a very naive question, building on that idea. So although you have a focal lesion, an area, I say naive because I don't understand really anything about EEG. And I just want everyone to know that. But it's kind of like a network level analysis, right? And so although it's a focal lesion, there's network level changes. And so is the ERN the same thing in a person post-stroke as it is in a person who hasn't had a stroke?
I mean, I think you look at classic electrodes for the waveform that you're interested in. So, but it's not necessarily network because it's just like these 3 or 4, we're going to look at those because those are usually what show the effect. So,
Right, but like they're not reading from only from a specific brain, right? Like they're reading from a bunch, you're getting sort of net
well,
electrical reading.
but the analysis is usually, I mean, it's usually like, I know Anna probably can speak to this, because I'm like you, I don't know anything about it. But I think you put less, for example, you put less credence in the more frontal electrodes because you have a lot of the orbital ocular activity, right? So there are many parts of the brain that you do not have a strong confidence in reading those waveforms, and so you just have these classic sites that you use. So, Anna, do you have more to say?
Yeah, I can add a little bit more, I guess. Well, the electrical activity that's measured with EEG, it's basically always, between two electrodes, right? So the voltage will be always between, so it's a relative value, right? And yeah, so again, this lesion location. So yeah, one more thing I wanted to add is that studies with individuals with brain damage have shown that the ERP effects more generally, that it's possible, first of all, to detect ERP effects, but then second of all, they are often either shifted in time, or they have slightly different location, or they have a smaller amplitude. So we see some difference, which may be because of the particular lesion location, but it's it's still possible to record the electrical signal that will be meaningful from those participants. I'm not sure if that answered the question, but hopefully we did it a little bit.
Good, great. I think we have to stop. Thank you so much. This was wonderful.
Thank you, everyone.